imagine for a moment how much of our modern world runs on tech we don't even really see. Things like, medical scans, advanced transport. What if a really core part of that, something like a magnet, could be completely revolutionized? Making these crucial tools, stronger, easier to get hold of, maybe even opening up whole new applications. Well, today we're diving into exactly that kind of breakthrough. It's a new, really efficient magnet design from two German physicists, Ingo Rehberg and Peter Blumler. We've been looking at their recent paper in Physical Review Applied, so our mission today. To unpack why this compact new magnet setup is causing such a stir, how it's actually a big improvement, and what kind of surprising impacts it might have. We're talking things like potentially slashing the cost of medical gear to maybe fueling the next wave of high-tech stuff.
Yeah, and to really get why this is a big deal, you first need to understand the need for what we call homogeneous magnetic fields. Basically, really uniform, even fields. These are sort of the unsung heroes in a lot of advanced tech. Everything from cutting-edge science research to, essential medical diagnostics relies on them. For ages, the standard solution, the go-to, has been the classical Halbach array. It's actually a pretty clever concept.
Okay.
You arrange magnets in a specific pattern so all the magnetic force gets focused on one side, making it strong and uniform there, and really weak on the other, almost like magic.
Right. Sounds neat. So if it's that clever, why isn't it the perfect solution everywhere? Where does the Halbach array fall short in practice?
That's the snag.
Yeah.
The Halbach array, its ideal performance, it assumes something that's, impossible.
Okay.
It assumes you're using magnets that are infinitely long, but in the real world, you build them with finite sizes, right? And when you do that, the magic fades, as they say. The field strength isn't perfectly even anymore. It wobbles. And the array just can't deliver that top-tier uniformity you need for the really precise stuff. That's been a real hurdle.
Okay, so that limitation, that sort of practical wall they hit, how did these two physicists, Rehberg and Blumler, come at it differently? What's their fresh approach?
Well, the innovators here are Dr. Peter Blumler at Johannes Gutenberg University, Mainz, and Professor Ingo Rehberg at the University of Bayreuth. Their idea was to figure out the absolute best way to arrange really compact permanent magnets in 3 dimensions. They started theoretically by thinking of magnets almost as perfect little points of magnetism, point dipoles we call them, to really optimize the layout.
Right, and managing that with permanent magnets, avoiding those huge superconducting ones, that sounds like the key achievement here. How exactly did they pull that off? What's the trick in these new arrangements?
Yes, exactly. The genius is really in rethinking the 3D arrangement. They look specifically at layouts that would be useful in practice, like single rings of magnets or even 2 rings stacked on top of each other. And what's really clever is this focused design concept. It means they can generate these super uniform fields outside the magnet structure itself. So you could place an object, say, above the magnets and still get that perfect field. That's crucial for a lot of potential uses.
Interesting.
And importantly, this wasn't just theory. They backed it all up rigorously. First, they developed the math, the analytical formulas for these new setups. Then they actually built them to test the predictions. They, got their hands dirty. They constructed arrays using 16 small, powerful magnet cubes. The specific type is neodymium iron boron, FeNdB, each just 20 millimeters on a side.
Wow, okay.
And they mounted these carefully on 3D printed holders. The measurements they took of the magnetic fields, they showed excellent agreement with what the formulas predicted. So the concept holds up in reality. They give a concrete example, too.
Right.
One of these focus systems with 2 stacked rings, each with 16 of those little magnet cubes.
Right.
It has an inner diameter of about 160 millimeters, and it creates a magnetic field of 20 millitesla. That might not sound huge, but the key is the homogeneity.
The uniformity.
Exactly. It's uniform to within about 0.5%, 5 per mil. Technically, across a pretty decent-sized spherical area, 50 millimeters in diameter. And they make it clear. These new configurations really do outperform the classic Halbach array, and even the modified versions people have tried, both in terms of the field strength they can achieve and that critical uniformity. It's a new benchmark, really.
Okay, so clearly a big step forward technically, but let's bring it back. What does this actually mean for people? Why should you, listening now, care about, better magnets?
Well, probably one of the biggest potential impacts, maybe the one with the most global significance, is with MRI machines.
Yeah.
Magnetic resonance imaging.
Right.
Current MRI tech, the standard stuff, it uses these incredibly powerful superconducting magnets. They're complex, they need extreme cooling, often with liquid helium.
Which makes them hugely expensive, right?
Hugely expensive, both to buy and to run. They work by creating strong fields to align hydrogen nuclei in your body tissue. Then radio waves nudge these nuclei, they give off signals, and computers turn those signals into detailed images.
Okay.
But the problem is, precisely because of that cost and complexity, MRI machines are, and I quote the researchers here, hardly available in many parts of the world.
Yeah, that makes sense.
So this new design, using permanent magnets but achieving much better homogeneity than before, it offers a really promising contribution towards developing alternatives. Imagine if you could build effective MRI machines that are dramatically cheaper and easier to maintain. The global health implications. Making that kind of diagnostic tool accessible could be massive.
That's a really powerful idea, making that kind of life-saving tech more democratic, more available everywhere. But are there trade-offs? Is this new permanent magnet design likely to completely replace the big superconducting ones, or is it more for specific uses?
That's a really good point. It's probably not a complete replacement across the board, at least not yet. The researchers frame it as a promising contribution, especially for things like lower field MRI systems.
Okay.
Traditional superconducting MRIs can still generate much stronger fields, which can mean faster scans or more detail for certain very complex cases. But for a huge range of diagnostic needs, particularly in places that currently have no access, systems based on these improved permanent magnets could be absolutely game-changing. Better performance, much greater accessibility.
Got it. So a major potential impact in healthcare. But you mentioned it's not just MRI, right? Where else could these improved magnet designs make a difference?
Absolutely. Anywhere you need strong, uniform magnetic fields, these concepts could be relevant. The paper specifically calls out particle accelerators.
For fundamental science research.
Exactly. Tools that help us understand the universe. And also magnetic levitation systems.
Maglev trains and things like that.
Potentially, yes. Think about future transportation faster. Maybe more efficient, maybe greener. Better permanent magnets could play a role there too.
So it really is a fundamental physics breakthrough, but with these potentially very tangible, very real-world consequences, from making healthcare more accessible to pushing science forward, maybe even changing how we travel. It's about democratizing advanced tech, isn't it?
That's a great way to put it. So just to recap quickly, we've seen how these two physicists, Rayberg and Blumler, came up with a new way to arrange compact permanent magnets to get superior, more uniform fields.
Outperforming the old standard.
Right, outperforming the classical Halbach array and its variations. And critically, they proved it works experimentally, bridging that gap between theory and practice.
So this isn't just about, a slightly better magnet in a lab somewhere. It feels bigger. It's about potentially making technologies that were once incredibly expensive and complex, well, much more widespread. And that leaves us with a thought, maybe something for you to ponder. If the basic building blocks of really complex systems like these magnets become radically cheaper, radically more efficient, what completely new things might become possible? What kind of access to critical tools might open up that we can't even really imagine today?